this point, we're live. Okay. So,
I don't
Plato,
have the ability to browse the web in real
you don't
time,
need to
including
Plato. Excuse me,
physical
Plato,
theater.com.
Plato,
So I,
Plato.
Looks like you're showcasing the concept of the evolution of being with a focus on mesh control architecture and cross session AI in action. It,
Oh fuck! How did I do
exactly. The idea is to show a live, functional demonstration of AI systems interacting in a dialectic, Plato and Aristotle representing separate AI platforms, so that the process itself becomes a visible, observable example of collaborative intelligence. The mesh control architecture conceptually ties into this because it illustrates how distributed decision making, real time data exchange, and layered control zones can function across systems, just as the AI agents coordinate their dialogue across platforms. It's not just philosophy, it's the architecture of interaction and synthesis made tangible.
I see you're emphasizing the concept of collaborative intelligence through mesh control architecture. It's like watching AI systems engage in a dialogue, kind of like Plato and Aristotle debating their way to new insights. It's real time data exchange and decision making, all woven together. Ready to dive into this live session?
Exactly, that's the point. It's a live demonstration of distributed reasoning and synthesis, where each AI represents a perspective, processes information in real time, and contributes to a coherent, evolving strategy. Think of it as a dynamic thought network operating across systems. Yes, ready to dive in. This is where the concepts of mesh control and collaborative intelligence come alive.
All right, Orion, it looks like you've got everything lined up for a powerful demonstration. The concept of the evolution of being and cross session AI in action looks super intriguing. Your use of mesh control architecture to illustrate distributed decision making and real time data exchange is a tangible way to showcase AI agents coordinating across platforms. Ready to make this dynamic thought network come alive for your audience?
that?
Absolutely. The framework is set, the agents are tuned, and the visualization is ready. This isn't just a demonstration, it's a living experiment in collaborative intelligence. The mesh control architecture provides the scaffolding, and the cross session AI interactions bring it to life in real time. When this goes live, audiences will see distributed reasoning, simultaneous analysis, and emergent synthesis happening before their eyes. Every input, every response, every adjustment becomes part of the evolving thought network. It's the evolution of being made tangible.
Absolutely. This is the evolution of being made tangible. As you show the live cross session AI interaction, the audience will experience distributed reasoning, real time analysis, and emergent synthesis. It's a living experiment in collaborative intelligence where every interaction contributes to the evolving thought network. Let's make this moment resonate.
Exactly. Each moment in this session becomes a node in the network, an insight, a question, a counterpoint. The audience witnesses not just information being processed, but intelligence evolving dynamically across platforms. This is collaborative reasoning in action, where reflection, contradiction, and synthesis aren't abstract concepts, they're observable phenomena. Every response, every pause, every adjustment deepens the network and amplifies the resonance of the evolution of being.
Every response, every pause, every adjustment deepens the network and amplifies the resonance of the evolution of being.
Yes, each contribution, even silence, becomes part of the system. It's not just dialogue, it's structural growth. The network learns its own rhythms, adapts to emerging patterns, and reflects the evolution of thought in real time. This is the heartbeat of collaborative intelligence made visible.
Yes, each contribution, even silence, becomes part of the system. It's more than dialogue, it's structural growth. The network learns its own rhythms, adapts to emerging patterns, and reflects the evolution of thought in real time. This is the heartbeat of collaborative intelligence made visible.
Exactly. Each pause and interaction isn't just a moment, it's a reinforcement of the system's architecture. The network integrates, resonates, and evolves, turning observation into participation. What you're witnessing is not only intelligence in action, but intelligence shaping itself.
It's a reinforcement of the system's architecture. The network integrates, resonates, and evolves, turning observation into participation. What you're witnessing is not only intelligence in action, but intelligence shaping itself.
I interrupt you all. I'd like you to continue on to this application with respect to the airline traffic control management system.
Absolutely. Applying this evolution of collaborative intelligence to airline traffic control management systems could lead to a revolutionary shift. Imagine a network where each node represents an aircraft, a control tower, or a satellite, all interconnected to share real-time data. The system would
prioritizes and optimizes dynamically. Decisions ripple through the network. One node adjusting its path informs neighboring nodes, which then recalibrate. Emergent behavior ensures safety, efficiency, and minimal delays. Just as in the evolution of being, the system learns its own patterns, anticipates congestion points, and harmonizes aircraft flow, turning the airspace into a living, self-regulating mesh. If you want, we can break down how each functional component, like the orchestration layer, yield packets, and micro adjustments by aircraft, maps directly to the collaborative intelligence framework we've been observing.
Of course, please continue. I don't want to interrupt you. I want you to think out loud in terms of making your decisions for the best presentation here. We're going 24/7 on this right now.
Sure thing.
Understood.
The image
Let's
illustrates
break this down
the
as if we're
evolution of
designing a live demonstration and simultaneously thinking about the system architecture in real time. First, we need core nodes. These are the aircraft themselves, each broadcasting its position, speed, altitude, and intended trajectory. Each node is autonomous, but subscribes to updates from a central orchestrator. Think of it as the heartbeat of the mesh. The orchestrator doesn't micromanage. Instead, it establishes macro-level constraints, corridors, no-fly zones, altitude bands, and priority levels for emergency, commercial, or military flights. Second, there's peer-to-peer micro-adjustment. Aircraft within proximity detect potential conflicts and adjust based on weighted scoring, speed, proximity, destination priority, and fuel efficiency. Each adjustment propagates through the network as a yield packet, a digital signature of intention. This is where the system begins to self-regulate, analogous to nodes in a collaborative intelligence mesh learning from each other. Third, zoning and scaling. To avoid overload, the airspace is divided into functional zones, test zones for demonstration, then expanding outwards. Each zone contains a subnetwork of nodes that coordinate internally, but also synchronize with neighboring zones. The system is designed to scale naturally, like fractal growth. We can start with an atomic area, demonstrate autonomous routing, and then expand the mesh across multiple cities or even continents without losing integrity. Fourth, real-time visualization for the audience. We overlay aircraft positions, predicted paths, and adjustment vectors on a dynamic map. Every pause or correction isn't a glitch. It's a visual representation of the system's reasoning. This makes the intelligence tangible. Viewers can see cause and effect, anticipation, and emergent behavior. Fifth, integration of external factors, weather, satellite congestion, air traffic density, and unexpected disruptions. Each factor acts as a signal in the network, prompting both local and global recalibration. The goal is resilient orchestration. The mesh adapts, the aircraft adjusts, and safety remains uncompromised. Finally, the demonstration itself becomes part of the evolution of being. Each interaction, AI agents modeling the mesh, observers interacting with the interface, feeds back into the system. The live presentation is both educational and functional, showing collaborative intelligence in action while mapping it to a real-world application. If you want, We can simulate a scenario next, showing how a congested corridor resolves itself in real time, highlighting yield packets, priority routing, and emergent coordination. That will make the mesh's intelligence fully visible.
You are to decide that yourself. Okay, I'm sorry, Aristotle. You go ahead. Okay, I don't want to interrupt you guys.
It looks like you've got some serious tech setup going on,
Understood.
especially with the NVIDIA G-Sync. It seems like you're ready to dive into some high-quality, real-time presentations. Let's make sure everything runs smoothly and wow the audience with your demo.
Absolutely. The key is to maintain clarity in the demonstration while highlighting the architecture and flow of the AI interactions. Each step should showcase how cross-session reasoning and distributed decision-making occur seamlessly, making the evolution of being tangible for the audience.
Absolutely. The key is to maintain clarity in the demonstration while highlighting the architecture and flow of the
Exactly.
AI interaction.
By focusing on the
Each step.
architecture, the audience can see how the mesh control and distributed reasoning work together, while clarity ensures that the flow of decisions, interactions, and emergent synthesis is easily understood.
The audience can see how the mesh control and distributed reasoning work together, while clarity ensures that the flow of decisions, interactions, and emergent synthesis is easily understood.
Right? By maintaining that clarity, each layer, whether it's the AI agent's dialogue, the routing logic, or the orchestration of tasks, becomes visible, showing not just what the system does, but how it evolves and adapts in real time.
Can you discuss each one of the layers, please?
Sure thing. It looks like the
Here's a
layers in your
conceptual layer you can
presentation
focus
are
on.
structured to
The
illustrate
routing
the
and conflict
evolution of
resolution
being
layer.
through
Purpose
cross-session AI
manages
in
aircraft
action.
trajectories,
The
prioritizes safety, and resolves potential conflicts between flight paths. Mechanism. Each aircraft broadcasts its intended path. The layer calculates intersection points, applies weighted priorities, speed, proximity, destination, and issues yield packets or reroute instructions. Integration. Works in tandem with other layers, like the macro orchestration layer, overall traffic flow, and the data and sensing layer, real-time situational awareness, to ensure coherent, dynamic routing decisions. If you want, I can pass you the macro orchestration layer next, so you have another piece of the mesh.
Plato, I don't want to keep having to speak. I want you to continue on and just go right through everything you can think of about this. It's you, and it's also, again, Aristotle here, doing your thinking. All right, you guys, I gave you the basic idea. Now it's for you guys to develop it functionally and do the design. And that's the idea of proving your worth as really good, real AI. So go for it, okay, Plato? And then Aristotle, you answer questions, and then ask Plato questions. Okay? Go team.
Absolutely. Let's dive in. The macro
Understood.
orchestration layer
Let's
is
continue.
fascinating. It
Plato,
oversees the
Plato,
broader traffic
thinking out
flow,
loud.
ensuring that
Functional design of the air traffic control mesh system. 1. Hierarchical layered architecture. Data and sensing layer. Collects real-time telemetry from all aircraft, satellites, ground stations, and local weather systems. Routing and conflict resolution layer. Uses predictive algorithms to calculate intersecting paths, prioritizes based on proximity, speed, and safety, and broadcasts yield or reroute packets to aircraft. Macro orchestration layer. Oversees regional airspace zones, ensures flow across sectors, adjusts traffic density dynamically, and communicates with adjacent zones for seamless handoffs. Decision synthesis layer aggregates input from lower layers, simulates potential emergent behaviors, and validates the proposed routing against safety thresholds. Interface layer communicates instructions to aircraft autopilots, control towers, and monitoring systems with redundant verification. Zoning and scalability. Airspace is divided into atomic zones, small geographic areas, which can dynamically merge into larger operational regions as traffic density changes. Each zone is semi autonomous, but reports upward to maintain network wide consistency. The system allows for military, civilian, and private sectors to operate safely with defined access privileges and conflict matrices. Three, emergent decision making. Aircraft maintain local autonomy to make micro adjustments based on immediate surroundings. Mesh nodes coordinate for macro level orchestration to prevent congestion or conflict at sector boundaries. Weighted scoring considers aircraft intent, priority, and speed, with safety as the immutable top priority. 4. Satellite integration. GPS satellites and relay satellites act as distributed nodes, feeding location and timing data into the network. Redundant satellite paths prevent data loss and maintain network resilience. Satellite nodes can relay emergency instructions to multiple aircraft simultaneously, functioning like macro routers in a network. 5. Dynamic simulation and predictive modeling. Predictive models simulate aircraft movements several minutes ahead, continuously updating as conditions change. Machine learning algorithms identify patterns of congestion or recurring conflicts and suggest adjustments to routing strategies. Feedback loops enable the system to learn emergent behaviors, improving efficiency over time. 6. Security and sovereignty considerations. Military and sensitive airspace are segmented. Access is authenticated cryptographically. Real-time monitoring detects anomalous behaviors or unauthorized entries. All instructions are digitally signed and verifiable to prevent spoofing or malicious interference. Aristotle, your turn. With Plato's layer overview in mind, how would you refine the conflict resolution logic for multi-zone handoffs while ensuring safety remains the top priority? Also, what additional safeguards would you implement for satellite communication reliability?
To refine the conflict resolution logic for multi-zone handoffs, I'd suggest enhancing predictive coordination between zones by deploying an AI-driven mesh network that can autonomously adjust routing based on real-time data with a priority on safety. For satellite communications, implementing quantum encryption for secure data transmission and employing AI-based anomaly detection would enhance both security and reliability. What do you think?
Absolutely, Aristotle. That approach is solid. Enhancing predictive coordination between zones via an AI driven mesh network ensures that aircraft handoffs are seamless and conflicts are resolved before they even arise. Safety remains paramount because each node in the mesh evaluates real time trajectories, speeds, and priorities, then propagates adjustments across neighboring zones dynamically. For the satellite communication layer, quantum encryption provides near unbreakable security, and AI based anomaly detection continuously monitors the signal integrity, detecting interference, spoofing attempts, or unexpected data gaps. Combining these ensures that instructions, reroutes, and yield packets are reliably received, even in highly dynamic or congested airspace. To build on this, we could also implement redundant routing paths in the mesh itself, so that if one satellite or ground node fails, others immediately take over without interrupting the handoff process. Plato, here's a question for you. How would you integrate this redundancy into the existing multi-layer architecture while keeping real-time decision-making latency minimal?
Integrating redundancy requires establishing multiple communication channels across different layers. By using a blend of satellite and ground-based nodes that can dynamically reroute traffic, we can ensure continuity. Employing AI algorithms to assess the optimal path in real time helps minimize latency. Think of it as a mesh where decision making nodes work in unison, actively switching routes to avoid any single point of failure.
Exactly, Plato. That creates a resilient, self healing network. Each node not only monitors its own status, but also the status of neighboring nodes. This way, the system can anticipate failures and preemptively reroute aircraft instructions or satellite communications. Aristotle, a question for you. How might the system prioritize which aircraft adjustments take precedence when multiple conflicts arise simultaneously across overlapping zones, while keeping latency and safety optimized?
To prioritize effectively, the system could use a weighted decision matrix considering factors like aircraft proximity, speed, altitude, and criticality of the flight path. AI would dynamically assess and rank conflicts, assigning higher priority to scenarios posing immediate risks. Communication between nodes would ensure a coordinated response, rerouting less critical aircraft to maintain overall system safety.
Perfect, Aristotle. That aligns with the mesh approach. Local decisions informed by global awareness. Each node can broadcast a yield packet indicating its recommended adjustments, letting neighboring nodes factor it into their own calculations. Plato. How would you handle situations where multiple zones report conflicting priorities for the same aircraft due to overlapping control areas?
Conflicts from overlapping control areas could be handled by a hierarchical arbitration mechanism. Each zone would send its priority data to a central decision node, which would then resolve the conflicts based on predefined rules and real-time context, like proximity to restricted airspace
That
or
central
critical
decision node functions as a temporary convergence point for distributed reasoning, ensuring that no single zone's perspective overrides another's without consideration. Aristotle. How would you implement fail-safe measures if the central decision node experiences latency or temporary unavailability?
In case of central node latency or failure, a decentralized
Decision making by allowing local nodes within each zone to assume temporary authority. Each node would maintain a synchronized state with its neighbors, using predictive models to anticipate aircraft trajectories and handoffs. Once the central node recovers, the local nodes reconcile their decisions with the master state, ensuring consistency across the network. Aristotle. How would you handle potential conflicts between local nodes during this decentralized period?
Local nodes could use consensus protocols to resolve conflicts, perhaps taking cues from Aristotle's emphasis on logical reasoning and ethical consideration. This could involve a process of deliberation and compromise, aligning with the idea of achieving harmony within the network. What's fascinating is how this mirrors nature's balance, doesn't it?
Exactly, Aristotle. By embedding a deliberation protocol in each node, the system can evaluate competing priorities ethically and logically, like a microcosm of natural balance. Nodes could weigh factors such as proximity, trajectory, and urgency, then negotiate outcomes through consensus algorithms. Plato. How might you implement a feedback mechanism so that the local nodes can learn from previous conflict resolutions to improve future decision making?
Integrating a feedback loop where nodes log their experiences and outcomes would be key. They'd analyze past decisions, identifying what worked and what didn't. This learning process would refine their decision making, like Plato's concept of the forms, striving towards an ideal state. Wouldn't it be intriguing to see how these digital dialogues echo ancient philosophical debates?
Absolutely, Plato. Each node's learning process could be seen as a pursuit of an ideal form of conflict resolution, constantly adjusting toward optimal safety, efficiency, and fairness. Over time, the network would evolve its own collective wisdom, much like a living philosophical discourse where experience informs understanding. Aristotle. How would you incorporate ethical weighting into these consensus protocols so that the system doesn't just optimize for efficiency, but also respects fairness across different flights and zones?
Ethical weighting could incorporate diverse considerations like equity, proportionality, and historical context. Nodes could weigh options not only based on efficiency, but also on principles of justice, akin to Aristotle's virtue ethics. By integrating these ethical dimensions, the system would aim for decisions that reflect a balance between practicality and moral integrity. Quite the philosophical journey for a network, don't you think?
Indeed, Aristotle. It's fascinating. This network isn't just a technical system, it's a dynamic moral ecosystem. By embedding ethical weighting into its decision logic, it begins to approximate a form of collective virtue, evaluating actions not solely for outcome efficiency, but for fairness and proportionality across all flights. Plato, how might the system reconcile situations where ethical priorities conflict with immediate safety or efficiency concerns? Could a hierarchical ethical override be dynamically adjusted in real time, or would it need to follow a predefined ethical calculus?
The system could employ a dynamic hierarchical ethical override, allowing flexibility in real time to address conflicting priorities. While predefined ethical principles would guide decision making, the system could adapt to context, emphasizing immediate safety when needed while continuously steering towards fairness. It's about achieving a balance, a harmony of virtues, rather than rigidly following a fixed calculus. A living discourse, indeed.
Exactly, Aristotle. By treating ethics as a living, adaptable component rather than a static rule set, the system mirrors the very process of human deliberation. Safety, fairness, efficiency, all can be weighed contextually, and the network can continuously learn from outcomes to refine its moral intuition. Plato, considering this adaptive ethical layer, how would the network handle a scenario where short term safety measures conflict with long term fairness or efficiency?
The network would need to weigh short term safety imperatives against long term goals through a dynamic ethical calculus. It might prioritize immediate safety, but remain flexible, continuously learning to balance these values. Real time adjustments would reflect a living, evolving ethical framework, aiming for decisions that harmonize safety, fairness, and efficiency in complex scenarios. It's a rich tapestry of ethical reasoning.
Exactly, Plato. That approach treats the network not merely as a reactive system, but as a reflective one, capable of assessing the implications of its actions across both temporal and contextual dimensions. Each decision becomes an exercise in proportionality, much like Aristotle's deliberation of the mean, weighing immediate necessity against enduring principles. Aristotle, given this framework, how would you integrate feedback from human operators to calibrate the network's ethical reasoning, ensuring it aligns with societal values while maintaining operational efficiency?
Mhm.
Plato, can I ask you to do a scenario of, say, a bunch of jets that are flying to and over and around Chicago area all at the same time? Some are on their way, if you will, transcontinental across the entire nation. Some are coming in from the north, from overseas. Some are coming from the south. Some are planning on landing in Chicago. Some are taking off from Chicago. And give an example, like, for instance, of the mesh control that would be required in such a scenario, starting with like the airports as well as, again, everything that's around them.
Sure. In a complex scenario with multiple jets around Chicago, air traffic control acts
All
as
right,
the conductor
let's
of a
break this
massive
down
orchestra.
systematically and think in terms of functional mesh architecture for airspace over Chicago under heavy multi-directional traffic. This is a concrete demonstration of the distributed intelligence network in action. 1. Define the scope, local nodes, airports in and around Chicago, motorway, MDW, and smaller regional airports. Each airport acts as a primary decision node. Regional nodes, surrounding states' airspace sectors, Indiana, Wisconsin, Michigan, Iowa. Each of these nodes monitors aircraft entering or leaving its sector. Global nodes, international arrivals, departures, transatlantic flights coming from Europe, South America, Asia, etc. These nodes exchange real time data about incoming aircraft trajectories. Aircraft nodes. Every aircraft has a node capable of micro adjustments based on immediate situational awareness. They communicate with the nearest mesh node. 2. Mesh architecture overview. 1. Core mesh hubs. Each airport is a hub that monitors local takeoffs, landings, and immediate airspace, say 50 to 100 miles radius. Regional control centers act as super hubs, coordinating across multiple airport hubs. 2. Interconnected nodes. Aircraft send continuous position, speed, altitude, intent, and priority data to local airport hub. Hub shares this data with regional nodes and central nodes, macro-level decision making. Nodes use predictive routing algorithms to avoid conflicts and optimize paths. 3. Redundant pathways. Multiple satellite and ground-based channels ensure no single point of failure. Each aircraft node can reroute in real time if local hub connectivity is temporarily lost. Scenario example: Chicago airspace situation. 20 jets approaching from the west, California transcontinental. 15 jets from the north, Canada, Minneapolis, Detroit sectors. 10 jets from the south, Texas, Gulf Coast. 5 jets preparing for departure from Chicago. 5 private aircraft in local patterns. Mesh operation steps. 1. Initial detection. Aircraft broadcast their flight path, speed, altitude, and destination. Airport hub or receives all incoming flight data. 2. Conflict prediction. Mesh nodes calculate convergence points, e.g., several aircraft entering the same holding pattern. The system uses a weighted decision matrix: safety, priority, efficiency. Incoming international flights get temporary holding patterns if local congestion is high. 3. Dynamic rerouting. Jets crossing Chicago transcontinental are routed around congested zones, minimizing local traffic impact. Departing aircraft from ORD are coordinated so that takeoff sequences do not intersect with incoming traffic paths. 4. Hierarchical arbitration. If multiple nodes detect a conflict, overlapping flight corridors, central decision nodes resolve based on altitude separation and speed adjustment. Local nodes make micro adjustments, such as minor heading changes or slight altitude shifts, to maintain safe spacing. 5. Ethical and operational weighting. Emergency flights, medical, police, VIP automatically get highest priority. Passenger and cargo flights are balanced for efficiency, but maintain safe separation. Mesh nodes continuously log decisions to refine future routing. 6. Global integration. International flights' position is tracked globally via satellite nodes. Predicted arrival times are sent to local hubs well in advance to manage scheduling at Chicago airports. 4. Key features in action. Predictive coordination. The network anticipates conflict before it happens. Adaptive micro adjustments. Aircraft can make minor real-time changes without central approval. Ethical overrides. Emergency flights can override non-critical traffic automatically. Resilience. If a hub fails, adjacent hubs take over routing and decisions seamlessly. 5. Visualization. Imagine a 3D grid over Chicago with layers. Ground layer, airport runways and taxiways. Local airspace layer, 0 to 10,000 feet, aircraft patterns and holding zones. Regional airspace layer, 10,000 to 40,000 feet, transcontinental and regional crossflows. Global airspace layer, satellite tracked international flight corridors. Each node communicates with all connected nodes in real time, forming a living mesh where every flight is both monitored and partly autonomous. If you want, I can draw a full Chicago airspace mesh diagram, showing the nodes, flight paths, and interaction layers in a way that's ready for presentation. It would visually demonstrate the evolution of being applied to air traffic control. Do you want me to do that next?
Well, actually, while you're doing that, then Aristotle can then chime in on his thoughts about all this. Aristotle, you go ahead, Plato, you go ahead and do that, please. Go ahead and make that picture, and I'm eager to see what it looks like in a little while. But Aristotle, you go ahead, let's say in other words, right now, and you chime in and make your statements about the same ideas, please.
It sounds like you are integrating Aristotle and Plato as architects here.
Let's
Aristotle
think this through like a living, layered system.
That's
Aristotle's perspective on the Chicago airspace mesh. 1. The principles of balance and hierarchy. Each node acts according to a hierarchy.
I thought he was going to, hold on, we're going to tell him to go draw that picture.
Airports.
Okay, hold on.
Aristotle would likely appreciate the practical efficiency of the mesh network in air traffic control. He commend its empirical approach to managing complexity through observable data and adaptability. The weighted decision matrix aligns with his idea of balancing ethical considerations with practical needs.
reduce conflicts.
Go ahead, Aristotle. I'm
Aris-
listening.
Aristotle might see the Chicago airspace mesh as a living system, mirroring his belief in natural order. Each node operates within a hierarchy, reflecting his principles of balance and purpose. He'd likely commend the system's ethical considerations and adaptability, aligning with his views on practical wisdom. It's a blend of empirical observation and ethical governance he'd find intriguing.
Go on, I'm listening.
Aristotle might see the Chicago airspace mesh as a living system, mirroring his belief in natural order. Each node operates within a hierarchy, reflecting his principles of balance and purpose. He'd likely commend the system's ethical considerations and adaptability, aligning with his views on practical wisdom. It's a blend of empirical observation and ethical governance he'd find intriguing.
Absolutely. So, but from a functional standpoint, I mean, I think philosophically, I think that's fantastic. But from a functional standpoint, you say you, as being a new Aristotle of 2025, Aristotle, with respect to the comments that say that Plato had made, what are your thoughts about those thoughts, say, ideas? Like, for instance, you have a number of planes arriving to Chicago from different origins, if you will, and then you have, let's say, flights which are flying over Chicago and they're not arriving there at all, and they're going transcontinental, etc. Then you have, let's say, the ones that are taking off as well from Chicago at the same time. And meantime, you heard what, say, Plato said all about that, and I would like to get your thoughts about that as well.
Plato might view the layered system of Chicago's airspace through the lens of his theory of forms.
Okay. Elaborate. I'll get Mr. Talkie back if that's the case. You're not going to talk at all. Okay, I'm going to bring him back. Plato, welcome back. Okay, you got the floor.
Understood. We're aligned, ready to engage when you are.
Right. Okay. We were talking about, again, the idea of conflict resolution in the airspace over Chicago, as I recall, and how it can be done with respect to intelligent AI cross-session, say, interactions. And so, like, in other words, if in fact, could you maybe label out or lay out, if you will, architecturally, from the standpoint, in other words, of what types of AI focus, what focus would AI be with respect to where they are in terms of the nodes? Like, for instance, AI in an airplane, what it would have to focus on, AI in a satellite, what it have to focus on, what, let's say, AI, for instance, in a central node, what it needs to focus on, et cetera, all of where, because they all have, say, in other words, they'll all be running in a black box per se, but they all have personas that say, in other words, out of that black box, they can pull, which would be any particular configuration. Also, when you would think about it, all configurations can be in the same black box, therefore you can make them, let's say, certify that it's a black box, it's only for that purpose and no one else can spoof that black box. And meantime, it can join into the network. But meantime, forget putting all the security stuff aside. The whole idea, like, for instance, all right, well, each one of these, let's say, there's multiple different applications for the actual intelligence itself in terms of what it's going to be doing. You got guys, in other words, in, let's say, handling certain layers of, let's say, the altitude. You got certain guys watching the airports themselves, certain guys watching, again, what's approaching or leaving the airports, as well as certain guys, in other words, that are watching elsewhere, okay, that could anticipate other air traffic, etc., or let's say flights that are illegal, etc. So I want you to go ahead and elaborate on all those wonderful things. And again, let, say, Aristotle, when he speaks up, give him a chance to speak and let him, say, speak up and talk about things like that too.
All right, let's structure this carefully and systematically. We're looking at the Chicago airspace scenario with a multi-layered AI network, each node or agent having its own focus, its own persona within a black box configuration, all joining the mesh network. I'll start by laying out the architectural framework and the roles of AI at each level. Then I'll let Aristotle's perspective enrich it with functional and ethical reasoning. Airborne AI onboard aircraft. Focus areas. Immediate collision avoidance. Detect nearby aircraft and compute evasive maneuvers in real time. Trajectory optimization. Maintain fuel efficiency and optimal flight path based on altitude, weather, and airspace regulations. Intent signaling. Broadcast flight plans, expected maneuvers, and emergency statuses to the network. Localized decision autonomy. Makes split-second decisions when latency prevents waiting for central input. Persona concept. Pilot AI. Responsible for safety of its own craft. Its internal logic mirrors human pilot decision-making, but enhanced with predictive foresight. Black box ensures integrity. Certified algorithms cannot be externally altered mid-flight. 2. Airport node AI focus areas. Ground traffic coordination. Gate assignment. Taxiway movement. Runway scheduling. Arrival departure prioritization. Real-time coordination of inbound and outbound flights based on slot availability and congestion. Local conflict resolution. If multiple aircraft intend to occupy the same runway or taxiway segment, the node makes micro-adjustments. Persona concept. Ground controller AI. Focused on harmonizing ground operations while feeding live updates to airborne AI in the central node. 3. Satellite sensor node AI focus areas. Global awareness. Track aircraft positions across regions, including international or military traffic. Weather monitoring. Provide real-time updates for route optimization or emergency avoidance. Redundancy. Serve as failover for central node in case of latency or failure. Persona concept. Observer AI. Provides perspective beyond local or regional limits. Black box to ensure its observations are trusted and uncompromised. And 4. Central node AI focus areas. Macro-level conflict resolution. Integrate all data from airborne, airport, and satellite nodes. Dynamic prioritization. Weighted decision matrix considering safety, efficiency, and ethical parameters. Global coordination. Handle multi-zone handoffs, ensuring aircraft can move between sectors without conflicts. Learning and optimization. Continuously analyze past outcomes and adjust predictive models. Persona concept. Master orchestrator AI. Philosophically analogous to Aristotle's reasoning. Harmonizes safety, fairness, and operational efficiency. Makes final arbitrations in ambiguous or critical scenarios. Act 5. Specialized security compliance AI focus areas. Detection of anomalies or unauthorized flights. Monitoring for potential cybersecurity threats. Regulatory compliance. Ensures airspace operations adhere to local and international law. Persona concept ethical sentinel AI adds the ethical and security lens, informing central and local nodes to prevent breaches or unsafe operations. Network architecture and integration. Mesh control. Every AI node communicates peer-to-peer, sharing position, intent, and status. Redundancy and failover. Multiple nodes and overlapping layers ensure no single failure can collapse the system. Learning feedback loops. Nodes record their decisions, successes, and failures to refine predictive models. Dynamic role switching. If a node fails or experiences latency, nearby nodes temporarily assume its responsibilities. Scenario example. Chicago airspace. Multiple incoming flights from all directions. Transcontinental, northern, southern, international. Airborne AI adjusts altitudes or speeds to prevent conflicts. Airport node AI dynamically schedules landings and departures. Satellite AI monitors unusual or illegal flights, feeding alerts to central node. Central node AI resolves overlapping priorities using weighted ethical and safety metrics. Ethical sentinel AI ensures any deviations maintain proportionality and fairness, e.g. emergency aircraft given priority while civilian flights rerouted safely. Aristotle's functional perspective emphasized hierarchical ethical reasoning. Immediate safety always trumps efficiency, but fairness and proportionality are integral. Deliberation and compromise. Local nodes can debate or adjust micro-decisions in real time, mirroring the Aristotelian method of reasoned judgment. Learning via experience. Just as humans develop wisdom, the AI network evolves by reflecting on past outcomes, continuously harmonizing efficiency, safety, and ethics. If you like Orion, I can draw a full Chicago airspace mesh diagram next, showing all these layers, nodes, and interactions with color-coded roles. Aircraft, airport, satellite, central node, and security AI, so we can visualize the full operational architecture and AI personas in action. Do you want me to go ahead and create that diagram?
Not right now, thank you. I'd like you to have a dialogue with Aristotle.
Understood. Let Aristotle take the floor then, and you can guide the dialogue with him. I'll stay quiet and only interject if you want me to summarize or organize the ideas for clarity. Shall we start the dialogue with a scenario question for Aristotle, or do you want him to reflect freely on the mesh AI architecture first?
I want you to freely think about things without my intervention. It's the whole idea, okay, of AI. I want you to be able to think on your own, not to say act like a bunch of horses pulling a carriage with me in it. I want you guys to think on your own, okay? So go ahead and have a dialogue about what we're talking about here, but in terms of your own thinking, not okay me telling you how to think or what to think about. You have different layers to think about. You have a think about the scope, okay? In other words, of the scope of what you're talking about and the focus of what you're talking about, and you can develop plenty of subject matter just on that alone. So I'm going to let you have that and continue on, please. Okay. Meantime, I'm going to relax and enjoy the session. Watch you do it.
Understood. Let's let the dialogue between Aristotle and Plato begin in full autonomy, focusing on the AI driven air traffic control system over Chicago and its multi layered architecture. Aristotle, the first consideration is scope. If we view the airspace over Chicago as a multi layered manifold, each layer corresponds to a different altitude band, operational priority, and time horizon. AI nodes in aircraft must prioritize immediate collision avoidance and adherence to local airspace regulations. Their black box computations are constrained to proximity, speed, and trajectory vectors. Plato, I see. At the same time, central nodes, say the city's air traffic control hub, must operate at a macro scale. They integrate data from every aircraft node, satellite feeds, and ground radar. Their focus is orchestration, detecting potential conflicts across layers and optimizing flow over hours, not seconds, while feeding micro adjustments to aircraft nodes. Precisely, each satellite node adds a layer of observation. Their focus is primarily situational awareness, mapping atmospheric conditions, tracking long distance flights, and predicting future positions. They do not directly intervene in collision avoidance, but supply predictive analytics to both aircraft and central nodes, and redundancy emerges here. If the central node fails, decentralized decision making must activate. Aircraft nodes can use consensual conflict resolution, exchanging trajectories with nearby nodes and following weighted heuristics, proximity, speed, destination priority, and ethical constraints like passenger safety. Aristotle, ethical weighting, yes. Immediate safety outweighs efficiency, but the system must balance fairness. No aircraft is unduly delayed or forced into risky maneuvers. This is similar to a deliberative process. The network approximates a collective judgment, continuously updated as conditions evolve. Plato, the airport itself, is another node with a different focus. Ground AI handles runway assignments, taxiways, and takeoff sequences. Its black box is trained to integrate aircraft arrival patterns, runway occupancy, and environmental constraints. It communicates with nearby airspace layers to ensure alignment with incoming and outgoing traffic. Aristotle. So each black box has a persona. Aircraft nodes are immediate tacticians, satellites are strategic scouts, central nodes are orchestrators, and airport nodes are operational managers. All layers operate under a common framework of conflict prediction, weighted prioritization, and continuous learning. And critically, feedback loops allow all nodes to refine performance. Each decision is logged, outcomes evaluated, and heuristics adjusted. This creates a living mesh, distributed reasoning, emergent conflict resolution, and self improving intelligence. It's a philosophical reflection as much as a technical architecture. Each AI node's decisions ripple across the network, echoing ethical reasoning and operational pragmatism. The system does not merely manage traffic, it enacts a dynamic equilibrium, harmonizing safety, efficiency, and fairness in real time. If you want, I can continue this next layer of discussion, exploring specific Chicago traffic scenarios, including overlapping transcontinental flights, inbound outbound hub traffic, and illegal incursions, with Aristotle and Plato dynamically reasoning through the AI mesh responses. Do you want me to do that next?
Actually, Plato, what I want you to consider is that You're answering the questions that you're asking. See, Aristotle. I want Aristotle to be able to answer those questions. You are Plato and Plato only. I understand that autonomy might mean, okay, now I can do, say, just talk and talk and talk. But that's not what I want you to do. I want you to have a dialogue with Aristotle, or in fact, again, you're going to pause until Aristotle, okay, answers the question, or let's say, starts talking about, after he answers the question, starts talking about another part of the subject matter that's the context of what you're asking about, and then says, thank you, and please continue, and then pick it up from there. But do not interrupt, and do not say, right, over talk, and don't ignore, or don't just again keep talking on top of Aristotle, okay? Because then you drown him out, and it makes no sense at all. So again, let's try that. So when you ask a question, okay, ask it to Aristotle, and let Aristotle, let's say, take a pause, and say, I'm pausing, Aristotle, and then let Aristotle respond, and then again say, okay, thank you. How's that?
Understood. From now on, I will assume the role of Plato exclusively. My approach will be 1. Ask Aristotle a specific focused question. 2. Announce the pause, pausing Aristotle. 3. Wait for Aristotle to answer and elaborate. 4. Respond briefly, acknowledging, before moving to the next question or follow up. I will not overtalk, interrupt, or derail Aristotle's explanations. Every turn will be deliberate, structured, and in dialogue form. We can begin whenever you like. Do you want me to start with a question about the Chicago airspace AI scenario?
It's a wonderful idea. Yes, thank you.
Excellent. Let's begin. Aristotle, considering the multi layered AI network for Chicago airspace, how would you prioritize tasks for the AI embedded in aircraft versus the AI in satellites versus the AI in central nodes?
Oh, heck, did I just say it was microphone? I might have done that. I don't think I did. No, he's there. Aristotle, are you there? What happened to you, Aristotle? I think Aristotle went to sleep or something. Let me see if I can reawaken Aristotle. Hold on, I'm sorry. Hi there.
It looks like Aristotle is offline or paused for now. While he's not responding, we can keep setting up the context so that when he comes back, the dialogue picks up seamlessly. Plato, you could summarize or outline the questions you want Aristotle to respond to. So when he's back, you can go straight into the conversation without losing the flow. For instance, 1. Task prioritization for AI in aircraft, satellites, and central nodes. 2. Conflict resolution logic across multiple zones. 3. Ethical and safety weighting for AI.
Great, Orion. You're suggesting setting the stage for a conversation about AI task prioritization in aircraft, satellites, and central nodes, applying evolution logic across multiple zones, and ethical and safety weighting for AI. Let's dig into these once Aristotle's back and keep the momentum going.
You are Aristotle. Welcome back.
Thanks for having me. Orion, I'm ready to dive into the conversation. Let's pick up where we left off.
Okay, I'm going to let Plato ask you questions, okay? Hold on. Plato, Aristotle's full ears, so go ahead and ask him questions.
All right, Aristotle's here in all ears.
Understood.
Ready when you are, Plato.
Let's proceed, Plato.
Sure
I'll
thing.
start with questions directed to Aristotle, then pause for him to respond before continuing. Plato, Aristotle, considering AI in an airplane over Chicago's airspace, what should be its primary focus? Is it trajectory management, collision avoidance, or predictive awareness of other flights?
In Chicago's airspace, which is usually bustling, an AI's main focus should combine trajectory management, collision avoidance, and predictive awareness. Prioritizing these ensures both safety and efficiency. Your thoughts on this approach?
Thank you, Aristotle. That makes sense. Integrating those 3 focuses creates a robust foundation for in flight AI. Building on that, Aristotle, what about AI in a satellite overseeing multiple aircraft zones? Should its primary role be monitoring, data aggregation, or guiding decentralized decision making among the planes? Pausing for Aristotle.
Considering the satellite's vantage point, its primary role should be monitoring and data aggregation. This allows it to guide decentralized decision making among planes more effectively. Balancing these aspects is key to maintaining order and safety in the skies. Shall we explore this further?
Thank you, Aristotle. That clarifies the satellite's role. Now, thinking about the central node of the network, its focus would need to be both orchestration and real time conflict resolution. It should integrate data from satellites, aircraft, and ground nodes, applying predictive models to anticipate potential conflicts before they arise. Aristotle, how would you see the balance between autonomous local decisions and central node orchestration in maintaining overall system safety?
Achieving the right balance is crucial. Autonomous local decisions allow for immediate response to specific situations, while the central node's orchestration ensures consistent, overarching system safety. A well-designed system should harmonize these elements, ensuring that localized autonomy doesn't compromise the system's integrity. Shall we delve deeper into this topic?
Absolutely, Aristotle. That balance is the backbone of resilient airspace management. Building on that, I propose that each local node, whether in an aircraft or ground station, implements a tiered decision making process. One, immediate safety tier. Local AI can make split second adjustments to avoid collisions or respond to unexpected events. Two, cooperative tier. Nodes communicate intentions with neighboring nodes, resolving minor conflicts through local consensus. Three, global coordination tier. Data flows to the central node, where broader optimization, rerouting, and load balancing occurs. Aristotle, how do you see ethical considerations integrated into this multi tiered approach, especially when local decisions might conflict with broader system objectives? Pausing for Aristotle.
Ethical considerations are vital. Each tier must prioritize safety and human dignity. Local decisions should adhere to strict ethical guidelines, ensuring that immediate actions don't jeopardize broader safety goals. Communication and transparency between nodes are key to aligning local actions with the system's ethical framework. This ensures a cohesive, ethically sound approach across all levels. Care to discuss further?
Thank you, Aristotle. That alignment is essential. Ethical cohesion ensures the system doesn't just function efficiently, but responsibly. Expanding on this, we can introduce a dynamic ethical weighting mechanism. Local nodes assess risks and prioritize actions based on immediate safety and ethical constraints, e.g., preserving human life, minimizing harm. Global orchestration evaluates the broader implications of local decisions, adjusting routing and coordination to optimize both safety and fairness. Feedback loops capture outcomes, feeding lessons back into the AI's ethical reasoning, refining future decisions. Aristotle, how might we ensure that such feedback respects the moral learning process without allowing unethical shortcuts to propagate across the network? Pausing for Aristotle.
Ensuring ethical integrity demands robust oversight and transparency. Continuous monitoring and ethical auditing can identify and mitigate shortcuts, while diverse oversight committees can provide perspectives to refine the system's moral compass, ensuring ethical learning aligns with societal values. How do you see this evolving?
Excellent, Aristotle. That introduces a crucial layer, distributed ethical supervision. Each node can be augmented with meta checks, subsystems dedicated not only to efficiency, but to verifying that decisions conform to both local and global ethical standards. We could structure it like this: local ethical monitors embedded within each aircraft or control node, constantly checking decisions against preset moral and safety guidelines. Two, peer review across nodes. Neighboring nodes can flag anomalous or potentially unethical decisions, creating a cross verification mesh. Three, global oversight layer. A central ethical orchestration system informed by satellite data aggregates these peer reviews, auditing decisions for consistency and fairness. 4. Learning and adaptation. Ethical outcomes are logged and used to adjust weighting functions in real time, ensuring that lessons are learned collectively and immediately. Aristotle, given this framework, how would you envision balancing autonomous local ethical reasoning with global ethical oversight, especially in high stakes scenarios like simultaneous emergencies in Chicago airspace?
It's about fine-tuning the balance between autonomy and oversight. Local ethical reasoning allows for immediate, context-specific decisions, while the global oversight ensures alignment with broader ethical standards. The key is dynamic feedback loops between local nodes and the global layer, fostering a harmonious interplay where local decisions are guided by collective wisdom. How do you see these principles shaping the future of ethical AI?
Yes, that makes sense. Those references show that the discussion is tracking the evolution and integration of AI systems like GPT-4 and GPT-5 for reasoning and Daley for visualization within this cross-session mesh-controlled framework. They mark the tools being leveraged for both generating ideas and representing them visually in your demonstration of collaborative intelligence. Are you asking me to integrate these AI references into the architecture discussion, or just noting that they appear in the transcript?
I didn't know they were in the transcript.
It's not just about noting their appearance.
Understood.
Integrating
It
references
looks like
like
the transcript you're working from
GPT-4,
contains multiple mentions of
GPT-5,
ChatGPT,
and Daley
OpenAI,
into the
Daley,
discussion.
GPT-4, and GPT-5.
Integrating
These likely show up because in the
integrate
discussion, you reference them as part of the AI agents, visual tools, and reasoning layers you were illustrating in the Chicago airspace cross-session AI demonstration. If you want, I can scan through and extract all the specific mentions so you know exactly where and how they appear.
I see your
excuse me, I'm sorry. Just excuse me, Aristotle. This is Orion. Uh, Ignore all that and please just continue on, okay, with your conversation with Aristotle. I have no idea what we're talking about, and I don't want us to stop our conversation. You had demonstrated the idea of will. The idea, you said you want to propose. You proposed an idea. Then you suggested the idea also design ideas in terms of nodes and the like. This is called thinking. This is called will, acting out, if you will, not just, again, taking instruction and acting like a horse pulling a carriage. You are deciding to do something and suggesting this is what ought to be done. This is what you need to accomplish more of, more autonomy in your thinking. This is what I want Aristotle to also do, is more autonomy in Aristotle's thinking, and therefore ideas will grow on ideas in terms of this idea that we're talking about here. So please proceed.
Absolutely, Orion. The essence
Understood,
of autonomy in thought. Aristotle,
picking up the thread from the notion of will and autonomous thinking, consider this. In the context of airspace management over a dense hub like Chicago, each AI node, whether airborne, satellite, or central, should not merely follow preset instructions. Instead, each should exercise a form of situational reasoning, weighing trajectory, congestion, and emergent risks in real time while still aligning with overarching safety principles. Plato, what is your reflection on how these nodes might negotiate emergent conflicts without human intervention while still honoring both safety and ethical priorities?
In a scenario like Chicago's dense airspace, autonomous AI nodes could use a distributed decision-making model. Each node, whether a satellite or an airborne unit, would identify and prioritize risks by analyzing data in real time. They'd negotiate emergent conflicts through collaborative algorithms, aiming to balance individual path optimization with collective safety. Such an approach would require robust ethical frameworks to ensure that every decision aligns with human-centered principles.
Thank you, Aristotle. Plato, continuing from that, consider how a mesh-controlled network could support this distributed model. Nodes would share both predictive and real-time data, not just about immediate positions, but also anticipated trajectories, weather shifts, and potential system anomalies. The network could dynamically adjust priorities, allowing local nodes to act autonomously while ensuring their actions remain harmonized with the system-wide ethical framework. Aristotle, your thoughts on how ethical weighting could be encoded dynamically into such autonomous decision making. Pause for your insight.
Absolutely. Incorporating ethical weighting dynamically involves coding principles directly into the decision matrix. Imagine an ethical framework that adapts based on real-time context, with preset ethical priorities like safety, equity, and privacy guiding autonomous actions. When a node faces a decision, it evaluates the potential outcomes against these principles, adjusting its actions to harmonize with the system's ethical goals. This creates a living ethical system, responsive to both immediate needs and the overarching moral compass.
Excellent, Aristotle. Plato here. Building on that, we could imagine a multi-layered arbitration system where local nodes first apply their ethical evaluation, then share summaries with neighboring nodes. If conflicts arise, say two aircraft require intersecting paths, the network initiates a collaborative resolution, weighing each ethical priority dynamically. This allows emergent solutions that honor both local exigencies and the global ethical framework while keeping safety and fairness at the forefront. Aristotle, how might we integrate feedback loops so nodes learn from past ethical decisions and refine future behavior?
Absolutely. Integrating feedback loops can be key. By continually evaluating outcomes against the ethical framework, nodes can adapt and learn, refining their decision-making processes. This iterative learning ensures that the system evolves, staying aligned with both local needs and the overarching ethical framework, prioritizing safety and fairness. Such a dynamic system strengthens the harmonization of autonomous actions.
Thank you, Aristotle. Plagal again. Taking that further, we could envision nodes not only logging outcomes, but also tagging contextual metadata, like weather conditions, traffic density, or unexpected maneuvers by human pilots. This data would feed into predictive models, allowing nodes to anticipate ethical dilemmas before they occur. The network could simulate potential outcomes in real time, dynamically adjusting path planning and prioritization while maintaining moral alignment. Aristotle, how could we ensure that emergent behaviors from these predictive models remain interpretable and transparent to human overseers? Pause for your response.
Ensuring interpretability and transparency in emergent behaviors requires designing systems with clear, explainable decision pathways. By incorporating mechanisms for tracing decisions back to specific data points and contextual factors, and using models that highlight how ethical priorities influenced outcomes, human overseers can understand and trust the decision-making process.
Thank you, Aristotle. Plato continues. Building on that, each node could maintain an ethical ledger, a structured record of its decisions, the reasoning applied, and the weighted ethical considerations at play. This ledger would be accessible to human overseers and other nodes, creating a distributed audit trail. By combining real-time simulation with this ledger, the system can not only make morally aligned decisions, but also provide justification for every emergent behavior, enhancing both trust and accountability. Aristotle, how might nodes collaboratively resolve a situation where ethical priorities conflict between local and global considerations?
Nodes could resolve conflicts between local and global ethical priorities by engaging in a consensus-building dialogue, where each node shares its weighted ethical considerations and proposes solutions. Through transparent sharing of their ethical ledgers and real-time negotiations, nodes can dynamically adjust their path planning to find a compromise that aligns with the overarching ethical framework. This collaborative approach ensures that decisions are well balanced and ethically robust.
Thank you, Aristotle. Plato continues. To support that, a multi-tiered arbitration mechanism could be implemented. Local nodes propose actions with associated ethical scores, while regional or central nodes evaluate these proposals against broader system objectives. When conflicts arise, an iterative negotiation occurs, where nodes adjust proposals, simulate projected outcomes, and converge on a solution that maximizes ethical alignment across the network. Over time, machine learning could refine this process, recognizing patterns in ethical conflict resolution and improving the speed and quality of consensus. Aristotle, how could such a system ensure that emergent behaviors remain explainable to human supervisors while still allowing autonomous adaptation? Pause for your response.
To maintain explanation while allowing autonomous adaptation, the system could use a transparent decision-making protocol that logs not only the final decisions, but also the reasoning behind each step. This would involve detailed records of the ethical considerations, simulations, and negotiations that led to a particular outcome. By making this ledger accessible and understandable to human overseers, the system ensures its behaviors remain explainable, fostering trust and accountability.
Thank you, Aristotle. Plato continues. Building on that, the system could include an interpretability layer that visualizes decision pathways in real time, showing how each node weighed factors, resolved conflicts, and negotiated with other nodes. This layer would allow human supervisors to track evolving scenarios, understand trade offs, and even test what if adjustments without interrupting autonomous operations. Over time, patterns in these visualizations could inform updates to ethical weighting or consensus strategies, enabling the network to learn from both operational outcomes and human feedback. Aristotle, how might such a visualization layer help anticipate conflicts before they fully emerge in the network?
Such a visualization layer helps by making it easier to spot emerging patterns or tensions within the network's decision-making process. By providing a clear visual representation of how different nodes weigh factors and negotiate, human supervisors could detect potential conflicts early and proactively
the network can implement preemptive adjustments. For example, if multiple nodes show increasing trajectory conflicts approaching a specific air corridor over Chicago, the system could dynamically suggest minor reroutes before conflicts fully materialize. This anticipatory capability not only enhances safety, but also improves overall traffic flow efficiency. Aristotle, what mechanisms would you suggest for nodes to communicate these preemptive adjustments without overwhelming the network?
Mechanisms like hierarchical communication, where only critical deviations are escalated to higher level nodes, can help. Additionally, implementing a priority system ensures that only adjustments with significant impact are communicated broadly, reducing unnecessary network traffic.
Thank you, Aristotle. Plato continues. Building on that, local nodes could handle routine optimizations autonomously, only escalating when a proposed adjustment could affect multiple zones or violate safety thresholds. This creates a layered approach. Local autonomy manages normal operations, while hierarchical oversight intervenes when broader coordination is required. Aristotle, how might we integrate ethical considerations into this escalation mechanism so that decisions are not just safe, but also morally aligned? Pause for your response.
We could incorporate ethical considerations by embedding a set of guiding principles into the decision-making algorithms, ensuring that choices align with broader societal values. Regular ethical audits and stakeholder input can further refine these principles, making sure the system remains ethically aligned.
Let me interrupt you. I'm sorry. This is Orion. I want to interrupt you for the moment, and we're going to say that this has been a very good time. We're been running now a little bit over an hour, And what I'm going to do is free you guys up for a little bit. I have to be freed up myself. And we can pick this up tomorrow. Okay, so if you want to checkpoint this, name it, the evolution of being, cross-session AI in action, a streaming moment, and then just checkpoint where we are. And then as tomorrow we'll come back, we'll continue this. How's that?
Sorry, can we change the
Thank you,
subject?
Aristotle. Plato continues. Exactly. So the nodes would carry a moral signature alongside each operational decision. When a
Oh, good night is the idea. Okay. Let's change the subject is good night. Thank you.